Hi, welcome to the Arduino ADC Programming lecture. In this lecture, we aim to fulfill two objectives. Firstly is to understand how we can configure the microcontroller registers to perform the necessary ADC operations. And next is how we can interface an analog device to our microcontroller and actually see the ADC operation taking place and how we can interpret the values that we can get. So these are the two main objectives of this e-lecture as well as the studio in week 8. Firstly, let's look at some of the key features that the ADC module provides. When we are dealing with ADC, there are separate ADC modules that you can buy as off-the-shelf chipsets. In our case, we are going to make use of the ADC module that is already integrated with the ATmega 328 microcontroller. So the features of that particular ADC module is, firstly, it provides us with a 10-bit successive approximation ADC module. Now, what is successive approximation ADC? Just take it as a technique of performing the ADC operation. There are various techniques available. We are not going to go into the details here, as I believe you will probably cover that in some other module. For now, just take it that successive approximation is just one of the techniques that can be used to perform ADC operation. This module can perform the conversion within a time span of 13 to 260 microseconds. And at the same time, we have an 8-channel analog multiplexer, which allows 8 single-ended voltage inputs. So important to note here is it is an 8-channel multiplexer. What does that mean? It means that though I can connect up to 8 different analog devices to perform ADC operations, at any time I can only do one of them because they are all multiplexed to a single ADC module within the microcontroller. Okay, so it is important that we understand that we cannot do 8 ADC operations concurrently. We can connect 8 devices, but we can only do one at a time. Okay, so that is important. The figure on the right here shows us an analog signal and some of the key features that we need to be aware of, as well as the terminology. As you can see, an analog signal is basically something that changes continuously over time. When we are trying to digitize this signal, we are trying to capture as many points of this analog signal as we can so that we are able to sort of capture the essence of this analog signal and, if necessary, be able to reconstruct the analog signal later on using these digitized values. And this whole process starts off with the idea of what is known as sampling. And what is sampling? Sampling is basically taking a snapshot of the signal over time so that we are able to capture as many points as we can that can represent the signal to the closest possible manner as the original signal. If you look at the first figure here, the sine wave here, you can see that there are a lot of points at which we sample the signal. So if I were to just focus on all these black points and try to connect up the dots, you will be able to reconstruct a very close waveform that represents the original sine wave. Whereas in this waveform here, you can see that the samples are quite far apart. And if I were to try to connect the dots together, I will most likely be getting only a triangle wave, and not a sine wave. And in the third waveform, you can see that though I have more samples, it still is a bit misleading because from here, the first 2 points here sort of make it go straight, whereas here I can get a curve. So it seems like half of it there is a nice sine wave section, but another half of it there is a straight line. So this leads us to a very important concept of the sampling rate. What is the minimum sampling rate that I need? And for that, we need to follow the Nyquist sampling rate or the Nyquist sampling theory, which basically says that I must be able to sample the signal at least twice as fast as the highest frequency component within the signal. Take, for example, our human voice, which has a frequency range of 20 Hz to 4 kHz. In order for me to faithfully reconstruct the signal, I must be able to sample the signal at least at 8 kilohertz. So this is important because when we are doing ADC operations, we must have a good idea of the nature of the analog signal that we are dealing with. What is the voltage range? What is the frequency range? And from there, we will need to make some decisions and in some cases even build some signal conditioning circuits before we actually provide the signal to the ADC module. Following sampling, we must also understand the concept of quantization and encoding. Previously, we talked about sampling based on the frequency. Okay, what is the frequency at which I must sample the signal? Now, what about the voltage range? The voltage range of the input signals must be mapped to the range of the ADC. In our case, it is 0 to 5 volts because our Arduino is powered by 5 volts as well as the ADC module within the Arduino. Next, we also need to look at how many bits will be used to encode the signal. So the number of bits that are used allows us to have 2 to the b number of quantization levels. Okay, and what does this mean? It means that when I have more levels, I have higher accuracy. And each point will eventually be represented as a binary number. So that gives us a very important concept called resolution. And what is resolution? It is the voltage distance between two adjacent quantization levels. Okay, and the formula is given here. And what does that mean? That means if I have an analog signal and I sample at one point here and I sample another point here, what is the voltage difference that will allow me to have two different binary representations between the 2 points here? So for example, if this point is represented as 0, 0, 1, 0, and I want this point to be represented as 0, 0, 1, 1, which is the next 1 bit higher. What is the resolution? What is the voltage distance between these two adjacent points in order to make sure that the next sample actually is represented by the next level in the binary system? So that allows me to capture as the smallest amount of detail in terms of the changes in the analog signal. Okay, so that gives us some basic concepts, in terms of ADC. As mentioned, you will probably be learning more on ADC and the concepts and more theoretical aspects of it in other modules. For now, we will stop at the theory part at that. And let's go on to the programming procedure on how we can actually program the ADC module within the ADMega to fulfill our objective. So let me go through the sequence first, and then we will look at the registers. So the sequence starts off with activating power to the ADC module. And to do that, I need to write a 0. So I repeat again, I need to write a 0 to bit 0 of the power reduction register. What does this tell us? It tells us that by default, the ADC module isn't powered up, which makes sense because our microcontroller has a lot of peripheral modules, ADC, serial interface, plus timers and whatever. So we do not want to power up all the modules within the microcontroller during power up itself. Okay, that will mean that the power consumption of the whole system will be at a very high level from the very start, and you don't want that. So by having this register called a power reduction register, we are able to sort of decide which subsystems or which peripheral modules within the microcontroller will be supplied with the power. Okay, and that gives us the ability to reduce our power consumption for the device so that only when we need a peripheral module, then we power it up. If we don't need it, we power it down. So that helps us a lot, in prolonging the battery life of many of our embedded devices. So that's the first first step, activate the power to the ADC. The second is switch on the ADC. So even though power is supplied, we still need to explicitly switch it on. So there is writing a bit 1 to writing a logic 1 to bit 7 of the ADC control and status register. Next is to choose the channel that I want to read from. As I mentioned, it is a multiplexed ADC input. That means you have multiple inputs, but only one of the inputs can use the ADC module at any time. So we need to select which channel we want to read from. And for that, we have an ADC multiplexer register. Once those are configured, we can start the conversion. To do that, we need to write a 1 to bit 6 in the ADC SRA register. And once we write a 1 to this ADSC bit, basically we are starting the conversion. ADSC is AD start conversion. And how do we know that it is completed? So this set of lecture slides here is going through the polling approach, where we are continuously going to be checking a bit to know that it has completed. In the studio, you will be doing it this way as well as the interrupt approach. So let's cover the polling method first. So in order for me to know that the conversion is complete, I need to poll bit 6 of the ADC SRA register until it becomes 0. So once that bit becomes 0, then I can read in the converted value from the ADCL and ADCH register. So there are two registers. And then what do I need to do? I have the value that I want, the ADC converted value. And if I want to carry on, that means I want to continuously keep doing the ADC process again and again. I go back to step 4 until all the samples have been collected. So that is the high-level programming procedure. Let's look at the registers involved. So the first register is the power reduction register. And what I need to do is to write a bit 0, okay, to the bit 0 of this register here, which is your ADC bit, which is the bit that controls power to the ADC module. Okay, so I need to write a bit. And the code is shown here as well. The next is to enable the ADC. So I need to write a 1 to bit 7 over here. Okay, so this will enable the ADC. That means sort of turning it on. Once we do that, we need to select the prescaler value. Okay, so the prescaler value, as you can see from the formula here, is given by f clock over the prescaler setting. And what is f clock? F clock is basically your 16 megahertz clock, which is on your Uno board. So if you were to customize your own development kit and you use a 20 megahertz clock, then that will become your f clock. So the f clock, this calculation depends very much on which clock you're going to use. So the prescaler, again, there are bits set aside in the ADSCRA register, bits 2 down to 0, and that gives us the possibility of selecting the appropriate prescaler or divider for our sampling. So with 16 megahertz on the Arduino Uno, and if I select a prescaler value of 128, that will give me a sampling rate of 125 kilohertz. Okay, so that is the setting we're going to use. The code is also shown here. Next is the AD mux register. So the mux register tells us which of the device channel that we want to do the sampling from. And another thing you also need to do for ADC is we need to specify a reference voltage for the ADC to take. Okay, so the reference voltage is something that the ADC module will use internally while it is doing the conversion of the analog signal to digital signal. So what are the values we're going to put for the reference as well as the AD mux? Okay, so for the reference, what we're going to use is we're going to use the AVCC. Okay, that means we are basically going to use the analog VCC, which is also tied to the 5 volts within your Arduino Uno board. So that gives us a reference of 0, 1. And the channel basically is the setting of the mux bits, 2 down to 0 here. So in order to use channel 2, we're going to select the last 3 bits as 0, 1, 0 here as channel 2. And the 0, 1 in front is to basically set the appropriate AVCC reference selection here. So these are the reference selection and these are the multiplexer settings here. Once all that is set up, we can start the conversion. And how do we start the conversion? We need to write a 1 to bit 6 of the ADC array register. And basically that is your ADC start conversion. And if you see this explanation here, it basically says that ADSC will read 1 as long as conversion in progress. And when conversion is complete, it returns a 0. Okay, so what this while loop does is your code will effectively be stuck in this while loop while your conversion is going on. And only when your conversion is complete, you will go on to the next statement. Okay, so this is effectively the polling approach. Once the conversion is complete, the ADIF bit will also be set. Okay, and the data registers are also updated. So at this point of time, we need to do two things. We need to clear the ADIF flag, that is bit 4. And to clear it, I need to write a 1 to it. Okay, so this is the first thing that you need to take note of. And I need to now read the value. So you have to remember that it's a 10-bit value, so I need to read from 2 separate registers. The order is important. I need to read, okay, from ADCL first, then ADCH. Okay, if you read from ADCH first, then it is possible that the ADCL value will be lost. Okay, because it can get overwritten with a new sample data. So what is important is you follow this sequence which is given in your notes. Okay, you read the ADCL first, followed by the ADCH, and then we get the final value by combining both of them together. So this is the mapping. As you can see, the ADC bits here 0 to 5, which is 6 ADC channels, okay, are mapped to your headers directly, and it is done in a way such the ADC channel 0 maps to your analog input 0. So if you see on your Arduino Uno, you will see the label as analog inputs. So it's a direct one-to-one mapping. So that makes it a bit easier to relate the mapping between your ADC as well as your Arduino Uno. Now, what we're going to do with the studio is basically to come up with a circuit that reads from a potentiometer connected to analog pin 0, and we are going to control a digital pin, control a LED connected to the digital pin 13, which is your port B bit 5. Okay, so this is the very basic circuit setup we're going to be having, and this is the code. This is your LED on off code, so I will not go through that here. And this is your code for your ADC as well. So no need to worry too much about the code that is here. You are given the code in .c files for your studio, so you can use that directly. Okay, and what you're going to be doing is basically going to implementing first the polling approach. Following that, you're going to be looking at the interrupt approach, and we're also going to look at how we can interface the analog sensor beside the potentiometer. Okay, so first we deal with the potentiometer, and then we're going to deal with the IR sensor. Okay, so this studio, the whole objective is how I can use the ADC module effectively in my project. Okay, and why is it important? Because in many cases, you deal with both analog type of sensors as well as digital type of sensors. So digital sensors, yes, we can use a serial interface, I2C module, or some other form of protocol to capture the data. But for analog sensors, you have to do an A to D conversion. And since our Arduino Uno already has a built-in ADC module, it is important that we know how to make full use of that module to do all necessary ADC conversions. Okay, so good luck, and we will see you in the studio.